So, Dr. Amin, correct me if I'm wrong, but since your background, um, you studied in Lebanon and then you went to Northeastern University where you did your PhD and research in particle physics. And I wouldn't be able to حتى say what specifically it is. But all I know it was in the Northeastern University, and then you moved to Germany to continue your research and teaching there. So what else can you tell us about that? How was it?
Yeah, exactly. Well, first of all, thanks for having me. It's good to be back. Exactly. Yeah. So I did get my PhD from Northeastern University in Boston, and I worked with Pranath, who is famous for supersymmetry and supergravity models in particle physics, basically theory. After 5 years, I moved to Germany to do my postdoc, and I'm into my third year now. I'm final year, basically. Yeah. So my research is in particle physics theory. In particular, during my PhD, I did work on supersymmetry, as I've mentioned. I'm glad to elaborate more on supersymmetry if you like. Some LHC also related physics, dark matter, and currently I'm more focused on dark matter studies and cosmology, in particular particle cosmology. So less supersymmetry now, more focused on cosmology,
dark matter.
Cosmology.
Wow.
And dark matter. Exactly. Wow. That's right.
Yeah. I think that's quite different from last time we spoke to you, right? Like, was that even 2 years ago, or was it last year? Last time we spoke, 2 years ago when we spoke, I don't recall, like, you were focused on dark matter as much. I think that's a recent shift. Sometimes when you hear the terms in the world of particle physics, they're very daunting, like supersymmetry, supergravity, dark matter. It's all very intense and it's all very dramatic as well. Like, I don't know what to expect. And when I first was learning physics at school, I remember I'd go through some of the history books where you'd find like crazy stories. For example, when what was the old model of like the planets and how they had like the Earth at the center? What was it called? Clomaic, something like that.
There's I forget the name.
I think the P is silent, but I can't. It's very difficult to say. But the model basically says that the Earth is in the middle and everything else is like rotating around it, and then they had the new model where we're rotating around the sun. And I remember reading in one of the history books they imprisoned Galileo and he was in house arrest, and then he said this thing, it pairs he move, still it moves. And then there's me 15 years old listening to some heavy metal album called A Percy Move, and just man, physics is incredible. But so how did we go from thinking Fenrir and Skranir swallow the sun when eclipse happen, and now we actually know what's happening?
Yeah, I mean, it took the bravery of a lot of people, as you've mentioned. Many scientists were prosecuted, like Galileo. And we have also many big names like Kepler. But I think the person who solidified the foundations of physics as we know it was Newton. So, of course, Isaac Newton did work on many aspects of physics, optics, mechanics, and so on. One other important thing was also mathematics. So he did invent calculus as we know it. In parallel with Leibniz, many people say, well, Newton stole it from Leibniz, but there is no real evidence about that. So I think calculus was invented in parallel, independently between the two men. But the modern calculus, or the calculus that we use now, is attributed to Newton, and he basically was the person to put the foundations for theoretical physics, because he was the first to say, well, okay, I have this observation. What can I write down on a piece of paper in order to make a model that can describe the observations, and not only describe it, it can actually predict future observations or future observations. So I think Newton was the person to set those foundations, and then of course from that point on we have this new language, which is a universal language that everybody knows, which is mathematics, and it took off from there, and we have our models, and then we try to sort of explain our observations based on that. Now, of course, mathematics took off in its own direction. We have, of course, pure mathematics, and that's also a realm of its own. But at least the engine in physics, the engine of physics is, of course, mathematics. That's how we speak this. And of course, many other great people came along, and we transitioned from classical physics that we use in every day, that even we use to go to the moon and to the other planets and explore space, to a new world, which is the world of quantum mechanics, which is the world of the very small. And this world, of course, has its own pioneers like Max Planck, Schrödinger, even Einstein. Those people, of course, are a league of their own. Up to this very moment, of course, we are still exploring physics and basically exploring the universe, what's around us, how things work, and how did the universe come about to be in the form that it is right now.
It's incredible when you say, the universal language is mathematics, and sometimes when you read the descriptions of those models, for example, and one of the models that always breaks my brain is when they speak about light, light, it moves this way, it behaves that way. When you put it in this experiment, it behaves this way. When you change the experiments, it behaves another way. And so when you look at the math, it's like, okay, man, I like the math, it makes sense. But then when you put words on top of the math, it actually becomes like, kind of extremely difficult to imagine what that means. So can you tell us a little bit about, how, in the example of light, how can it do such things? Like, how can the math say that it can be a wave, it can be a particle, and the behavior can be so radical?
Right. Well, for the light is a particular case, because the particle of light is massless, and it's the particle that we call now the photon. I think the first person to ever coin the particle property of light, that light is actually behave as particles, was actually Newton. But unfortunately, there was no evidence, there was no experiment, there were no experiments to support that claim. On the contrary, there were experiments actually to support the wave nature of light, that Thomas Young was the one to pioneer this. So Young said, well, all the experiments we're seeing around us supports the idea that light behaves as waves, like reflection, particle, light bouncing off mirrors or surfaces, refraction when light goes through another medium, like when it traverses water. There's other experiments, like, for example, polarization of light and so on. So all of these back in the 1700s or 1800s, they supported the fact that light behaves as waves. But it wasn't until the 1900s when the model for the photoelectric effect was discovered, and it was Einstein who coined the word photon to describe light as actually lumps of energy, which is propagating in space. So, and for people who don't know what the photoelectric effect is the idea that if you have a certain metal and then you shine light on it, the light is able to knock out electrons from the metal. And if you have a closed circuit, you can have those electrons go around the circuit, and you can turn on the light or any other, instrument. And of course, the photoelectric effect is something that is used a lot. But again, what's the answer to your question? What is light? Whether light is light particles or is it waves? It's actually both. And how do we know which one to use? That's a question, perhaps. It actually depends on the experiment. So as I was saying, that if you are dealing with the experiment like the photoelectric effect, you would need the particle model for light. If you're dealing with experiments like reflection, you would need the wave aspect of light. And it all actually depends on the size of the object that you are experimenting with when using light. So if the size of the object is comparable to the wavelength of light, you should use the wave model in principle. However, if the particle that you are examining, for example, under a certain emission of light, like under a microscope, or if the energy of that light is the energy of the particle is comparable to the energy of the light, then you will use the particle model. So the answer is actually depends on what experiment you're doing, and this is where you use the particle nature or the wave nature of light.
So it's almost like you have different lenses. Those doctors with the zoom in, and then you just kind of shift it, trying to solve the problems that you're trying to figure out.
Yeah, exactly. There's like an example of if you have like 4 blind people, and you ask them to touch a certain object and identify it. Let's say if it's a huge object, they would all disagree on what the object looks like, so they're touching a certain part of this object which is very pointy. They're touching an edge which is or a part which is flat, and so on. They would all say, well, for me it looks like that, for me it looks like that, but they're actually all touching the same object. And I think it's the same thing for light. It's the same object or the same phenomena, but it depends on how, if you're taking the touching part as basically the experiment. So it depends on what kind of experiment you're doing in order to observe the nature of light. It actually gives you, sort of slightly different results, but it's all the same thing.
Wow. And you're kind of able to see all those experiments. They all make sense together, right? They don't contradict each other.
No. Yeah, absolutely. There's no contradiction so far, because that's science, and we know that science, you can never say it's absolutely true. You can say that the experiment so far, supports the evidence, or that, X, Y, and Z behaves that way, and this is what we know so far. But you can never say, well, this is the ultimate truth.
Have there been any advancements in understanding light better? In the example you gave of the 4 blind people touching an object, not knowing what it is, or having different interpretations of what it is, they're limited by the tools they have. And so I'm sure if they had better tools, they'll be able to get an accurate representation of what it is that they're touching. So I remember this has been going on for a while, that we're not sure really what light is. Has there been any advancements, and could it be that knowing what the opposite of light is, would that help understand light even more?
No, I think we have a pretty good idea of what light is. I think this is now again, I'm trying to avoid using words as, well, it is settled truth now, or it's settled, I don't want to say that, but I think we have a good idea of what light is and how we can describe it, and it's all the entire spectrum of light, whether we're talking about visible light or we're talking about the other parts of the spectrum which is not visible. I think we have a good idea of what that is. But to answer your question about having better tools, of course, we can always have better tools. We can always improve the experiments. However, one should not forget that we are always limited when we with our precision, because if you get to the point where you hit the what I call the Heisenberg uncertainty principle, you can never know at this point. You can never tell 100% the 100% accuracy anymore. For example, in its famous form, the Heisenberg uncertainty principle tells us that if you know the position of a particle very well, you definitely cannot tell what its velocity exactly is. So if you have very high precision in something, you lose definitely precision in something else. So when you go to distances that small, we are going to hit this wall, which is the Heisenberg uncertainty principle. Definitely, we can do advancements in our tools, but again, there is a certain limit.
Like you were talking about how the Heisenberg theory, that's what it's called, right?
The Heisenberg uncertainty principle, yes.
Yeah, uncertainty principle. How no matter how much we advance as like our tools and as a human race, like how in the sci-fi movies, like they say everything's possible. So does this Heisenberg uncertainty principle is it always there, or will it ever be,
always?
Can never go past it, right?
No. That is a solid principle of in quantum mechanics, and in one of the famous books by Stephen Hawking, he says, again, whether you agree with him or not, but he says even God is bound to the uncertainty principle. So it is that solid of a foundation that you cannot overcome it.
That's a strong statement.
And that's because, so the way I understand that, things in the quantum realm, they're a bit like there's probability, there's nothing certain in quantum realm. Everything is like, we can predict the probabilities, and based on that, we'll make our deductions. I don't know if you can tell us about this experiment, but once I remember reading about an experiment that I didn't understand very well. And basically, it has to do with shooting an electron. So again, like the double slit experiment, and then but you close or open one of the gates after the electron has passed through, and that apparently changes the probability.
Right. I think, yeah. I mean, I think you're referring to the standard double slit experiment, right? So if you shine light on two slits, so again, the double slit experiment is simply so you have like a screen with two very small slits at a certain distance from each other, or the slits meaning like really, really small openings. And usually the openings are they have a width which is comparable to the wavelength of whatever particle you're using. And on the other side, there's a screen behind where you can actually see what's happening. So if you shine light through that slit, of course, you see all the pattern which is consistent with a wave. So you have the interference pattern where you have some bright spots and you have some dark spots and so on. So what they did is that they tried to do this experiment using particles. So those are like electrons, for example. And we know that electrons are actual particles with a specific mass and a certain energy and so on. So once you actually do the same experiment, you notice that you get the same pattern as you would for light. And this is which was very striking. Is that when you shine a beam of electrons through those slits, you get exactly the same pattern. So here, electrons are actually behaving as waves. And this is what is known as the particle-wave duality. of matter. So even small particles, I think they even tried it with neutrons, which are heavier than electrons, and it actually gave us the same outcome.
Wow!
But the most striking thing is that so you have those particles going through those slits, and then they are interfering with each other on the other side, and they're giving us this pattern. So they tried to look through which slit those particles are going through where they're interfering. And then they actually decreased the intensity of the particles going through. So instead of sending a bunch of those electrons onto the slit, they started sending one electron at a time. And they also saw the same pattern. So there's an interference pattern. So it does seem that the actual electron is interfering with itself to give you that pattern. Now, once you try and look at the particular slit to see in which slit the electron is going through or the photon is going through, the pattern on the wall behind the screen basically disappears. You no longer see a wave, the interference pattern. So that is, I think, what you're referring to, Amir. Once you try to do an observation on one of the slits to see where the particle is going, the particle basically no longer behaves as a wave anymore, and it starts behaving as a particle. So instead of an interference pattern on the screen, you will see one spot where you have particles impinging on that spot. And that is also, of course, related to the measurement problem in quantum mechanics and so on.
That is pretty shocking.
Yeah.
Yeah.
It's very crazy how you actually, it's so like the behavior of things in the quantum world, it changes. It's so sensitive. Like, oh, I'm observing your khas, I'm going to change my behavior.
I should say
I'm a people person. I'm used to dealing with just big things, but it's like Mabshi is I shine a light on something stiffy.
Right. I should say here a word of caution, because a lot of people like to take experiments in quantum mechanics or quantum physics and just tailor it into something which is a lot more into science fiction or things that are not true. It's not the conscious observation of that particle that makes it behave differently. So at a certain point in the history of physics, in the 1900s, I think it's all close in the 1920s, there was an interpretation which was going on amongst physicists that particles do respond to a conscious observer. So if you have only if you have a conscious observer, this is when the particle actually changes its behavior from being having a wave nature to a particle nature and so on. This is what is sometimes known as the collapse of the wave function. So every particle in every entity in quantum mechanics is described by this mathematical object, which we call a wave function. So from the wave function, you can actually tell a lot about the properties of the particle. And in particular, if you take the square of that wave function, you get the probability of finding this particle at a certain place. So what people started saying is that, well, if you do an observation and it, even if it's only if there's a conscious observer, this is when the wave function collapses or basically changes behavior. And this has been, of course, refuted over the many years, is that you don't need to have a conscious observer. It could be just a screen or a computer, like an electronic device that is doing the observation, and you get the same outcome. So I just want to say that because many people, I'm not saying you guys, like many people would think that way, and that would relate it to some, metaphysics kind of, things. There's been countless books written about the quantum mechanics and how, it's related to consciousness and to existence, human existence, and
So you're telling me you're telling me all the crystals I bought were for nothing?
Is that what you're doing?
You're telling me Ant-Man in the quantum realm is this fake?
I'm sorry to burst that bubble. I'm so sorry about that.
About the consciousness, I'm curious, in the current advancements in artificial intelligence, is this helping quantum physicists understand the nature of light and the cosmos better? I know you have to drink water for this one. Yeah.
So, okay, let me not jump immediately to artificial intelligence. Basically, maybe also using some other machine learning techniques or things that are very much more advanced than the usual tools for analysis that are used in particle physics. Machine learning, or if you want to call it some advanced or some artificial intelligence kind of, I shouldn't say artificial intelligence like analysis, but an analysis based on machine learning or things like that. They are very much common these days in particle physics, and they definitely have helped, and they are helping, and I'm sure that there will be many breakthroughs in that area of research. I have used a little bit of this in my research, but I cannot say I'm an expert in this area of research. But I know CERN, which is the biggest particle laboratory in the world, which hosts the LHC, the Large Hadron Collider, has, of course, as you know, tons of data that it produces every day, and sifting through this data and trying to decide what part of this data is interesting from the physics point of view, and which is just garbage that needs to be thrown out, is such a humongous effort and is such a humongous endeavor. And this is only collecting the data, because after collecting the data, particle physicists will actually work on analyzing it to try and dig through this whole debris of particles to see if there are some new particles that we have missed, that they're there, we don't know of, that can complete our theory somehow. So doing all that is very daunting, and I know that they have used a lot of machine learning tools which have aided basically in the discovery of the Higgs. So the Higgs discovery was based on a machine learning tool, which is, for experts, they know it's known as a boosted decision tree, which they use in order to do the analysis, and that's how the Higgs was discovered. AI is not really much at play now. It might be in the future, but again, I'm not an expert.
So what is the Higgs boson?
Well, the Higgs boson was actually it was the last missing piece of the standard model of particle physics. And so what is the standard model? It's a framework that particle physicists have put together of several theories that describes the fundamental particles in nature, in the universe, and how they interact with each other. So this is our framework. This is where we work. It's a set of equations, and it tells us, again, how particles interact with each other. And we have several particles in this description in the standard model. And the last missing piece that completed the picture was discovered in, in 2002 at CERN, which was the Higgs. So the Higgs is a particle that basically gives mass to the other particles. We have the common particles that I think a lot of people are aware of, like electrons. Again, there are many particles, but I'm talking about the fundamental particles, the particles that are not made of other smaller particles. So electrons, for example, and the quarks that make up the protons and the neutrons and so on. So those are fundamental particles, and they have mass. And their mass is very much all over the place. You have particles that are extremely light, and you have particles that are really heavy, which is like the top quark that was discovered at Fermilab in Illinois, in the US in 1996. It is a very heavy particle. And when you have a strange mass hierarchy here, you have all sorts of particles, and they have, as I said, their masses are all over the place. you need some mechanism to generate mass. So the big question was, how do these particles gain their mass? How do they acquire a mass? And the Higgs was the missing piece. The Higgs is the answer. So the Higgs field is the field that gives those particles their masses. And this is why it was a big deal when it was discovered.
I think I learned about the Higgs particle, and I think it was something to do with chemistry, and I think so, like something like that, about, like you said, the particle giving energy to other particles.
So, of course, in chemistry, we do deal with fundamental particles, I guess, like electrons. I believe this is a very common thing. And yes, an electron is one of those particles that gets its mass from the Higgs field, from interacting with the Higgs boson. So the boson is a type of particle. So the way the Higgs interacts with an electron, being very light, is different from the way it interacts with another particle, which is much heavier. Okay. I'm not sure who actually came up with this description, but I think it hammers home the idea of how Higgs, all the particles interacts with the Higgs. If you are, for example, trying to go into a room with one door, and you're trying to make it to the other side of the room, but this room is packed with people. So you try to make your way through this room, and you're interacting with a lot of people, and so you try and make your way through the room, but it's very hard, especially if you are a large person. However, a child might be able to make their way through the room much easier. So that room and the people in it can describe the Higgs field. So if you interact with the Higgs field more, you've gained more mass. So you have more mass, basically. Yeah. However, if you barely feel the Higgs field as you go through, you have acquired less mass. And this is the case of an electron, which is very light, versus, let's say, the top quark, which is very heavy. And the way they interact with the Higgs field decides what their mass is.
And the Higgs field is just, it's a field that's always there in the quantum realm.
So all fields are just, present in the space-time around us. And the Higgs boson is actually an excitation of this field. So you have the field, which is basically just a stagnant or a still sort of configuration in space-time. But when you excite this field, it creates this bump in it, which is what we call the Higgs boson. And what particle physicists do at CERN is they collide the protons at very, very high energy, which excites the field. And the excitation of the field causes those Higgs particles or the Higgs bosons to be produced. And of course, that Higgs, which is produced, lasts for a very, very tiny fraction of a second, and then it decays. So it decays to other particles. And by examining the decay products of the Higgs, we can tell that there was a Higgs there. So the idea is that you cannot detect a Higgs directly, but you can detect its decay products, and you can trace them back to the Higgs. And that's how we know its mass, that's how we know its spin, and many different properties of the Higgs.
Wow, that's a great explanation. I never really understood it, imagined it until you explained that. That's pretty great teaching. What's the significance of the Higgs boson? So we understand it now. It exists, the Higgs field. How does this advance our understanding of the universe?
Of course, it is. So again, there's a lot we know now about the Higgs than we knew before, like in 2002, then it was discovered. So we've been examining and studying the Higgs for now 11 years, almost 11 years. And we know more about the Higgs and the Higgs potential more than we knew before. But there's still a lot of unanswered questions. The main, of course, success or triumph in discovering the Higgs is that it completes our understanding of this of the standard model of particle physics. It completes this picture, and now we know that this particle is real, and it is the one that gives the other particles their masses. But there is also another story to the Higgs, is that the way it decays to other particles is not fully tested yet, and we need to test whether the decay of the Higgs to the other particles in the standard model that we know complies or matches the predictions of the theory. And this is a very exciting time, because if the decay, we call it branching ratios, or if the way it decays does not match 100% with the predictions of the standard model, then we may be up to a new discovery of some new physics somewhere. There might be something influencing this decay. So I think the importance of it, not only its discovery, but also how we're testing it as we go, and you try to sort of unravel all the secrets of this particle. Another aspect is the Higgs potential. So we know the Higgs potential mathematically should have a certain form, which usually like a sombrero, like a Mexican hat. It looks something like this with a bump and then goes up again. However, we know a little about this potential. We don't know different parts of it. Now, without going into technical details, or not much into the technical details of it, but we'd like to know where is the minimum of that potential, because it can tell us how stable the universe is. So it's a really scary thing if the universe is not stable, and at some point it can just decay. If the vacuum of the universe decays, then, well, we'll be in trouble. So we do hope that probing the Higgs potential can give us more answers on the stability of the vacuum that we live in. The vacuum meaning, the kind of universe we live in. We believe it's a meta-stable state, meaning it's not 100% stable, but it is meta-stable, meaning it is stable over billions of years. So the probability of tunneling into another state is quite small. But again, this is pure theoretical speculation. So we need some experimental evidence to know exactly if the vacuum decays or not.
You mentioned you're researching more dark matter. Does dark matter come into play when talking about the Higgs boson and trying to figure out if that vacuum is stable or not?
No, dark matter is slightly different. Dark matter has no known interactions with the Higgs, as we know, and this is actually an important question also in research currently. Is that does the Higgs couple somehow to dark matter? If it couples, it may decay to dark matter. And dark matter, because let me just maybe put it more into context. What is dark matter? So there is some invisible mass in this universe, which constitutes around 85% of matter in the universe. And it's striking that the matter that we see and that we know very well is only 5%. And this is called baryonic matter. So all the matter that we are made of and everything you see around you and you see through galaxies, peering into the universe is basically baryons, or ordinary matter that can reflect or emit light. Dark matter, however, which is much more abundant, around 85%, is dark, meaning it does not interact with light. So we know it's there because of its gravitational effect, but we cannot know its actual constituent, what it's made of. So if this dark matter, which let's assume it is a particle, again, there is no reason a priori to assume it is a particle, but as particle physicists, we like to have things made of particles, because that's good for us. It keeps us having a job and doing research. So let's assume it is made of particles, and if the Higgs decays into dark matter, that is something that can be discovered at the LHC, and that is definitely very exciting. So this is the only connection I could see between the Higgs and dark matter.
So there's no reason to assume that dark matter gets its mass the same way other particles do. It can get its mass in a different way if it were a particle.
Right. No, the dark matter could get its mass in a different way. It doesn't have to be through the Higgs. There are other ways. There could be also an additional Higgs, much heavier, that we don't know about, that can give the dark matter its mass. So there are many other mechanisms for which dark matter can get its mass. It doesn't have to be through the Higgs.
And so which part of the research are you mostly focused on when it comes to dark matter? What are some of the questions you're trying to answer?
Right. I mean, what particle physicists do in general, in theoretical particle physicists, we try to come up with a model that is an extension of our existing model, which is the standard model of particle physics, which can explain existing data and also predict new results that can explain something which we don't know much about, like neutrinos. Now, of course, we know about neutrino, but we don't know how neutrinos get their masses. So neutrinos, the way they get their masses is not part of the standard model. So that's one. Two, dark matter is also not part of the standard model. So also dark energy as well, and gravity. So focusing on dark matter.
Sorry, but what are neutrinos? Sorry.
Yeah, neutrinos are not part of the standard model. I mean, they are there, but they are massless. So according to the standard model, neutrinos are massless.
Where do they exist? Like, well, where? How do we know what's a neutrino?
Oh, okay. Yes, that's a question. So good. So there are some basically reactions that end up with ends up with a neutrino. For example, something that is called the beta decay. In radioactivity, you have some elements that are not stable, so they decay. And when Pauli was studying, I'm almost sure that it's actually Pauli. I hope I'm not getting this wrong. So when Pauli was studying those reactions, he was seeing that there's an imbalance. So their energy was not conserved. So the right-hand side and the left-hand side were not adding up in terms of energy conservation, because a neutrino is like a ghost particle. It escapes and you cannot detect it. So a neutrino is a very light neutral particle. It has no charge. So it cannot be deflected by a magnetic field. It cannot be affected by an electric field, and so on. So once it's produced, it just escapes without detection. So when Pauli was, is it Pauli or Fermi? No, sorry, it is actually Fermi. When Fermi was examining those known as beta decays, he constantly got an imbalance of energy from the left-hand side and the right-hand side of the equation. And then basically he said, well, there must be some particle that is escaping and carrying away that energy that we cannot detect. And he actually said this particle is a neutrino. And neutrino is like it's like a neutron, but in Italian, when you want to say that something is small or cute, you say it's a ino, like you put like an ino at the end. So he was like, well, it's like a neutron because it's neutral, but it's tiny and small. Maybe it's cute, so it's a neutrino. And that's how the name came about.
And I thought I was just really good at football. Neutrino, Ronaldinho.
Neutrino. No, I think this is from the Italian language. So, those are the neutrinos, and they are part of the standard model, as we said, and they are masses. And we thought they were masses for the longest time, up until we discovered something called neutrino oscillations, that actually neutrinos flip their flavor. So basically, they are of one kind, and they oscillate to another kind, and then they oscillate to a third kind. And only particles that have a mass can oscillate. And so we know now very well that neutrinos do have mass. but there is no known mechanism in the standard model to generate masses for neutrinos, and that's why it is a puzzle.
Wow.
Okay, so
I wonder what. All of us have questions. Yeah, exactly.
Go for it.
Go for it, guys.
So
I was
my
just
question is a bit.
yeah. I don't have a question so far. I just wanted to so just tell you my understanding, just to check that, because after all of that, so what I understood was there are some gaps in the standard model, and that have to do with neutrinos and how they interact and how they behave, and likewise for dark matter. And your role is kind of to answer those questions and connect them to the standard model,
or to extend the standard model in a meaningful way, so that it's now a theory that can explain all those observations that we know that we've seen, but we know we don't have a proper theoretical explanation for them.
Okay.
Yeah, that's right.
Yeah, so I was going to ask that when we're talking about dark matter, is it the same as saying antimatter, or is that a completely different topic? No,
it's different. Yeah, and I know that a lot of people confuse these. No, they're very different. So antimatter is just that same particle, but with an opposite charge. For example, an electron has an antiparticle, which is called a positron. So it's just like an electron, but with a positive charge. And antimatter was actually theorized to exist by Paul Dirac. Now I forgot, maybe in the I believe it's in 1926, if I'm not wrong. So when he was working on his equations in quantum field theory, he came to the realization that his equation is actually giving two solutions. Just like if you remember from school, you have a quadratic equation, and quadratic equation gives you like two solutions, right? And then you have to ponder whether those two solutions are accepted, or whether you have to throw out one and just keep one, and so on. So he was pondering whether those two solutions are actually physical, or he needs to throw one of these out.
Questions.
What's that?
I mean, for me, disconnect for you guys as well.
Mm-hmm.
Yeah, back now. Yeah. Amul, why is it always Abbas's questions, man? Whenever
too big, man.
Yeah. So Dirac finally came to the conclusion is that both solutions are acceptable, and one solution corresponds to a particle, the other one corresponds to an antiparticle. And years down, it was later discovered by Anderson in the lab that basically he discovered the positron, which is the antiparticle. So every particle has its antiparticle in principle. Now, dark matter is different. Dark matter has no charge. It's not charged. Does not interact with light. And so far, the observation is that it only interacts gravitationally. So it has no other modes of interaction, just like the other particles interact in the standard model. So it is a very different entity, and it's something that we actually see when you use telescopes and use other surveys. You can see dark matter. However, antiparticles or antimatter seems to have vanished somehow. You can only produce them in a lab, but we know they were created in equal amounts when the universe was created, almost equal amounts. You have maybe for every 1 million of matter, there was 1,000,001 for every 1,000,000 antimatter, there was 1,000,001 of matter. So the 1 millions annihilated together, because when you put matter and antimatter, they annihilate. And what was left was the matter particles. And that's what you see around us. So this is one of the biggest also puzzles and questions in physics. Why was there an asymmetry in between particles and antiparticles? Why was there slightly more matter than antimatter in the early universe, even though they should have been created equally? So this is a big question, how this came about. of course, dark matter is still a big question because we don't know
I
what
have
dark
so
matter
many
is made of.
questions, Matt. I've asked
Yes,
so many questions. Right?
there is a lot. There is a lot that we don't know.
So
we're very much ignorant at this point.
So saying if they were equal, wouldn't that mean, like, if they were equal, wouldn't there have been just nothing?
Exactly.
Oh,
there would have
okay.
been just nothing.
Wow.
So I have two questions about dark matter right now. So first of all, is it like when you detect dark matter in space, are there areas where there's like, oh, here we have like a bundle of dark matter and here we don't have as much dark matter, or is it like evenly spread out?
So usually dark matter is in places where you have structures, when you have galaxies or galaxy structures and so on. And the way it's perceived is that if you look at our Milky Way, the galaxy that we live in, there's a halo of dark matter around it. So there's a huge structure of dark matter, and this is again the sort of perceived notion of what is known as virialized dark matter. But there are also other ways we have seen dark matter through something called gravitational lensing. So what is gravitational lensing? It's actually the way light bends around massive objects. So if you've been following the James Webb Space Telescope and all the beautiful pictures that are coming out of the telescope, you've seen there are some pictures of a lensed galaxy, meaning so you have a galaxy in the foreground, but you can see two other like stars or galaxies on opposite sides, and it's the actual same galaxy, which is on the other side. So what happens is that when light is coming from that star, let's say this is a galaxy, a huge galaxy, and there's a star behind it, and this star is emitting light. So this massive galaxy will act as a lens, and we know that when you have a lens, you have light coming, and then light even
curvature,
diverge. So what we see, looking at those pictures, we see as if that star is in two positions behind that galaxy, whereas it's actually the one and the same star. But because of the gravitational lensing, as light bends over the galaxy, we see it in two opposite positions. So what astronomers have actually seen is that in some cases there is a certain bending of light around a mysterious object that we cannot say it's 100%, a galaxy which emits light, something that we can actually see, but there is definitely light bending around a mysterious dark entity. And we know that this, of course, is attributed to dark matter. So if you have a certain galaxy which also has some dark matter around it, the way light bends should be proportional to how much mass there is. And when you do the calculation, you see how much mass the star has. It does not add up because there must be some more mass there so that to bend light more. And this more mass, this extra mass, is actually coming from dark matter. So this is something called weak gravitational lensing. There are other observations from something called the bullet cluster, where you can clearly see that there is some invisible entity there that is causing. So the bullet cluster is actually two clusters colliding with each other, and as they go through each other, you can see the gas
clusters. What
a cluster is a collection of galaxies.
Okay.
So those two galaxies were colliding with each other, and you can see that there's a part of them that go through each other without even feeling each other. This part is the dark matter, and there's a there's a part of them that combine and lump together, and this is the gas or the baryonic matter that we call in physics, which is something that we can see. So the bullet cluster was really a smoking gun signature of the presence of dark matter out there in the universe.
Wow.
Wow.
Let me, I just want to look at, can you explain a little bit more about what we're looking at here in the James Webb Telescope? Yeah. So like this image, these images are what's coming out of it. You see what I'm looking at? Yeah.
Yeah. I should
So
put a disclaimer here. I'm not an astronomer, but I'll try to.
Oh.
I think the biggest one is the one which is called like a star nursery or something. It's the one that basically is a factory of stars. It's actually producing stars, these pillars of dust and so on. Yeah, I mean there are really fantastic images coming out from and as you can tell, there's more refined sort of details on those pictures that we didn't see from Hubble. Yeah, those are, we call these, they call them pillars of creation. As you can see, those are where we believe that this is where stars are being born or stars are created. I think I see the quintet down there. This is like a collection of 5 galaxies together. I'm not sure about well, there's some images that are exactly the same but different. No, it's the one on the bottom. Well, okay, now it's in the second row, the second one in the second row.
This one.
Yeah, it's something quintet, but it's the.
So what's going on here? Yeah.
So yeah, this is a collection of 5 galaxies basically that are in motion together. So their gravitational effect are influencing each other. So they are more in a coupled motion together. But I should tell you, those are like millions of light years apart from each other. This is like a huge structure. But they are huge galaxies that their gravitational influence is humongous on each other.
So all of what we're seeing is just like the matter that we can see. None of this is dark matter.
Yeah, this is baryonic matter. This is something that we can see. Yeah, exactly. By the way, I think the caption on this figure is wrong. They're saying it shows a star nursery. That is not really, but in any case, again, we should go back to the idea that we have to be careful when we are looking up things on the internet because not everything is 100% correct.
Yeah, it could be AI generated. James Webb
fabricated. Totally, right? Yeah, exactly.
Could be, yeah.
So those pictures we see, they're of the past, right? Like it's because of how long it would take light to travel. What we're actually seeing is what it looks like millions of years ago.
That's exactly right. You're just peering into the past. Yes.
Wow.
Incredible. Yeah. Man, I love listening about physics and I'll often like slip in like a book or two in my reading list just to go through them. And my friends, they always ask me like, what are you doing? Like, why do you have a book on like Richard Feynman lectures? Like I have that at home, and I'm like, look, man, everything in life, there's a lot of things that make me curious, but there's nothing that makes me more curious than physics. It's just whenever I listen to it, I'm like, where am I? What is this? Yeah. So it's always so fascinating, and it gives me like, and it helps me carry that curiosity elsewhere as well. Because you're looking at life from such a different perspective. You go into a different field, and now you're more curious about it as well. Because we're star particles, and then now all of a sudden, you're sat at a PC doing like some financial analysis, and and it's also like surreal. I'm kind of curious about both. Like.
Yeah,
so
that's great. I mean, I've been doing this for what now? 3, 5, 7, maybe 10 years now, doing this kind of research. And sometimes I read a paper or I read something on a topic, and I'm always like, I still get astonished and amazed on things that, especially in cosmology, like we have the ability, and you have to, whether you like math or you don't, whether you like physics or don't, you have to appreciate, or you have to at least sometimes just contemplate the ability that we have to write down an equation on a piece of paper, and then take that equation and do some simulations or do some tests and see that it actually predicts what nature looks like or what nature behaves like. Especially in cosmology, we can write down equations that tells us how the very seeds of structure formation, how galaxies were created out of perturbations from the early universe. Those equations can actually describe what we are looking at out there in the galaxy, out there in the universe. And it is striking. It is just amazing. Even if you're doing it for 10 or 20 years, I think you will always be amazed. Even if you are an insider, let alone an outsider of this field, I understand all the astonishment and the amazement that people feel and express. So yeah, very true.
It's a beautiful thing,
Wow.
and well, I like the when you first started, we were talking about models, and I remember reading something about so you mentioned two things. A model should be able to explain what's happening, and it should be able to predict the future. And I remember reading one more instruction. I think, I'm not sure from whom, to be honest, but I want to say Einstein, but I don't. ما بدي أفتي. I don't want to make that assumption. But so I think it was like it needs to be elegant, and maybe I'm extrapolating too much, but again, like from sounding like the pseudoscience of the consciousness relating to quantum physics. But I still would like to extrapolate and say, it's nice to have a model like that to explain also how you relate to things in life and how things outside of physics, and just like your own way of interacting with your daily life, and just having a model that's elegant. It kind of explains things in a nice way, and helps you predict the future. And I think for me, that's why I have an interest in philosophy. And it's also, it kind of helps you build a mental model of how to understand the things in life that aren't particles, great talk, man. This is blowing my mind. What would you tell
my mind is
people?
blown too.
Yeah. The idea of elegance just in our models is something that particle physicists, we like to have it. We like to think that the standard model itself, as we know, it is very elegant. It's a very elegant set of equations, a very elegant model. But when you try to extend it to include the other observations, it might get a little bit messy. However, we try from that perspective to keep it like that by exploiting some symmetries and so on, so that we keep it elegant. However, there's a sort of a big fight now in the particle physics community that maybe we need to abandon this principle, but that nature doesn't have to be elegant. Our equations, like you have parameters in nature that are extremely small, and you have parameters that are large. Why are they small? For example, why is the mass of the electron very small? Why is some other parameters the way they are? And we try to for example, the mass of the Higgs, as it's predicted by theory, it should be humongous. It should be astronomical in size. However, nature tells us that the mass of the Higgs is actually much less. In the words of particle physics, it's 125 GeV, which is a unit of mass. But particle physics, or the theory that we have, tells us it's much, much bigger. So this is one of the other problems that we try to sort of build the theory to explain why the mass is actually smaller and not humongous as our theory predicts. So there are attempts, but some people have in some way given up, saying that, we have to accept that some elements or some parameters in nature are the way they are. They just so happen to be like that. And that is known as the anthropic principle. So the anthropic principle is saying, well, okay, this is the mass of the electron or some other parameters. We have to accept them the way they are. We cannot know why they are the way they are. So we have to accept them. And I think there's a lot of pushback from particle physicists because we don't like that. But I believe that there's a lot of people who are proponents of the anthropic principle. This is just to sort of a side note on the comment about theories being elegant. Maybe they don't have to be elegant. Maybe they are really messy and we have to accept them. But I am not in favor 100% of the anthropic principle. Let me just say that.
Yeah. It's amazing though when you do explain things so elegantly, like the Higgs boson principle. We talked about a lot today, but the Higgs boson, I've heard about it and knew a lot about it, but you explaining it and giving examples and really making it clear, now I understand it a lot more and deeply. And then so I do think it is maybe another, you're researching all this physics, but to disseminate this information is like a huge responsibility and role too. Yeah, exactly.
Yeah. You have to, I think if you want to explain it to non-physicists in a way that it can be comprehensible, I think you cannot explain it if you don't understand it. And that's one of the things that Einstein and Feynman, used to say a lot, that if you cannot explain it to a child, for example, it means you don't understand it. And there are things that I struggle with in explaining to people because I try to use less jargon, less technical stuff as possible. But I think there's a certain limit. I mean, sometimes I need to include some mathematics. I need to include some jargon to explain it. I don't have the ability to explain everything in the simplest way. And I think even at some point, if you listen to the Feynman's interviews, he keeps on, digging deeper and deeper in that question up to a point where he says, "Well, I cannot explain it anymore. It's just as the fundamental thing. There are no words that I can use in the English language that will enable you to understand it. Because at some point you have to write down an equation, and this is where you get stuck at. But Feynman was unlike many others who was able to keep going down in depth of explanation, but keeping it very simple. And that's why he was the master of scientific communication. He is still, one of the biggest names, one of the masters out there. So, now he's deceased, but he's still regarded as one of the biggest names and one of the most prominent geniuses out there.
Well, we're wrapping up on time soon. Yeah, I don't know if you got me and Dr. AJ, do you want to ask a last question? Yeah.
I have so much, but no, I'm good for now. I asked.
I just want to say, what would you tell people who, young kids or like maybe teenagers trying to shift into a career in physics? What would you tell them?
Don't do it. Don't do it. Well, it is a very, there are many things that I did not know. In hindsight, have I known things, I might have done things differently maybe. But in any case, just regardless of any of these, if you're passionate about physics, of course you should do it. I was kidding. But maybe you have to be smart in selecting the topics that you would like to study. If you go into experimental physics, that is a big advantage. That is great. I have to admit, I am not very talented in experimental physics. I do not see myself in a lab. So that's why I went into theory. So if you decide to go into theory, you have to know exactly what topic to work on, because there are some topics that are very much, cutting edge or very very how do I say, not mainstream, but they're very important these days, like cosmology. So if somebody is into particle physics, I think my advice is to go into particle cosmology, especially if you are in the US. There is a lot of demand on particle cosmologists. If you are in Europe, there's a lot of opportunities to work on LHC physics and of course cosmology. And when I say cosmology, this also includes dark matter and dark energy. So yes, if you see yourself you're talented in this, you should go for it. It is a very rewarding field. There's a lot of hard work. I mean, going through a PhD is almost like a nightmare, but parts of it, I mean, looking back now, it's I just, looking back at my days during my PhD, I just smile. I have like really good memories, but it is very, it could be very stressful at times. Going through this is, it's a daunting task, but it's very rewarding. And the research you get to do and the people you meet, very talented people. So, you should definitely go for a career in physics, but you have to be sort of smart in selecting the topics that you want to work on.
Mm-hmm.
Just this episode is making me want to change to particle cosmology.
That's awesome.
Well, I mean, you will definitely end up making more money as a doctor than as a particle physicist. So I think you should stick to medicine. That's one other thing. Don't expect to be making tons of money as a particle physicist. So if you are really after, making a lot of money, that is not the field for you. So but of course we were chatting before we started that, and then there's even if you decided at the end of your PhD that you wanted to pursue something else, all the fields basically very much all the opportunities are open for you. You can do a lot of work in industry. You can do a lot of things like in data analysis or be a data scientist. That is something people like to hire physicists or mathematicians who have a PhD. Sometimes during your PhD you realize, well, this is not for me. I cannot do this for a living, and then I need to switch. So that is also there's a path where you can go to from academia to industry.
Mm-hmm.
Yeah.
I'm curious. My last question is, other than your field of research, what are some other fields of research that you're curious about and you're excited about the advancements that can happen in our lifetime? Yeah.
This is I feel like after having when I was teaching back in high school, I had like a lot of sort of knowledge about the different topics. I feel like after I've gotten my PhD, I became dumber. And the thing is that because I'm now like very much focused, because it's reality. When you do a PhD in a topic, you're very much focused on this particular topic, and you're an expert in it. But you no longer follow the other interesting stuff that is going in the field. But the ones that are closely related to quantum mechanics or particle physics and so on, I think I'm pretty much interested about quantum computing and quantum information. I think there's a lot of good work that people, mainly in the US, because this is where the main hub is, in Caltech and in other places, there's a lot of good stuff that people are doing, really breaking a lot of breakthroughs. In astronomy, also with the James Webb Telescope, there is a lot of things to look forward to that will also impact cosmology in our field in some way. There's been a lot of uproar on some galaxies that have been discovered, really distant galaxies, that in our model, in our cosmological model, we think that really distant galaxies should be smaller in size. But now the James Webb Telescope is seeing galaxies that are really far away, and they are massive. So now we don't know how those galaxies have acquired such a huge mass in such a short period of time. One, I should say, disclaimer is that those results have not been scrutinized exactly, so they might change. But as of now, those are the results. Some other fields, well, that's what some also things in neuroscience as well. Because I'm just thinking about the different groups back in my university, when I was doing my PhD, the kind of things that people were doing also in solid state. Really, there's a lot of interesting things that people are doing, but those are the ones that
they all combine with each other too. Yeah, like neuroscience and particle physics. It's interesting to see how the advancements in each will combine with each other to lead to something new. Yeah, exactly. And all of that together. Wow. Fascinating.
They could be all interconnected,
What an episode, guys. Well, thank you so much for checking out this episode. Thank you, Dr. Amin, again for your time. Dr. AJ, none of us are doctors except Dr. Amin.
I mean, you don't have to. Just Amin is fine. Yeah, thank you for having me, guys.
Teaching us for another lesson. Yeah, exactly.
And thank you again. Yeah.
Signing out. Let us know if you found this interesting. If you have more questions to the listeners, you can let us know and you can ask Amin and he will let us know the answers. All right. See you guys. Goodbye.
Bye.